the interruption. So please.
So kind of coming from seeing the problems while teaching computer science, I did a PhD on this topic, and yeah, kind of after the PhD went on postdocs, first in England, Utrecht, then kind of became assistant professor in Vienna, and now I'm professor in Karlsruhe. So you might kind of have picked up that having done my master's in mathematics and taught mostly mathematics and computer science kind of on the side and increasing, the differences and commonalities between the two is something that I'm just interested really from the beginning on. Just kind of to this point, some of you, so I'm not going to tell you exactly what kind of math you need for computer science, because I'm really approaching this much more from a philosophical level in a way. So kind of to say a bit where I'm coming from with this is, first, I found in my classes that some mathematical pre-knowledge leads to misconceptions of the students. Up to the point that some of my students, when I asked them to, hey, write a program to solve an equation, they would start by writing down the equation in the first line of the program, because that's what you do when you start kind of solving a math exercise. But then also the question came up, so if math and computer science are really similar, why do we have to introduce computer science and programming in schools? I mean, isn't that just kind of math in disguise? Do we really need both, or kind of what's the connection there? And that's kind of the background where I'm coming from with my talk today. So shall I start with that?
Well, maybe you could. Do you want to share the screen? You have.
Yes.
Well, but I think it's an interesting topic, though, and sometimes I think there could be quite different opinions on what's what here.
Yes, absolutely, and I mean, I certainly have to say, I think that there's a long discussion to be had about this. So I'm not claiming that I arrived at the final conclusion and this is it. So yeah, I'm kind of looking forward to any discussions afterwards. Perhaps kind of just I have to apologize a bit. I'm in one of these intelligent new buildings. So depending on how I move, the light will go on or off. So the lighting here, I can't really influence it. It's all completely automated.
That's technology for you.
All right. Let me start then. As I kind of already said, the topic is a bit kind of about mathematics and computer science. And I want to start with the question of what is time? And for that, let me start with a kind of a story from ancient Greek. So in ancient Greek mythology, there was Kronos, one of these gods in the early beginnings, who had children, one after the other. And each time kind of a child was born, he would swallow them and eat them away, until eventually the last children, Zeus, was able to kind of escape this fate. And once Zeus became kind of a man in a sense of grown up as a god, he went back and got all his siblings that came before him back from Kronos. And so together, kind of, they were then these deities of Greek mythology that built the Olymp and kind of ruled the earth, so to speak. Now, the question that I want to ask here is a bit, so Kronos is the god of time. So what we could really kind of, we could interpret this story in a way that Zeus was able to defeat time so that he and his siblings could all be together at the same time rather than live sequentially or something like that. And from that on, the question is, what concept of time do we have, or what concept of time is behind this story? This idea of I can defeat time and bring back what has already gone and kind of have it with me in a way. So on the one hand, it's kind of the question, what's the nature of time, but also how do we speak about time? How do we kind of, what kind of notions, what kind of words and so on do we use to talk about time? And perhaps kind of, we cannot really just bring back anything from the past, but a notion that's really very common in today's culture, in literature, in movies and so on, is the idea of time travel. So if you think about it, if you could travel in time, how would your journey look like? Where would you go? And what does it actually mean? I mean, could you go back and keep your parents from meeting and like in Back to the Future, or just kind of what concept of time do we have? Now, perhaps the first concept of time that we could think of is time as a flow. And with time as a flow here, I mean kind of the river that's stretched out. So again, you often see this in movies or something where kind of the timeline is something that's stretched out in front of you, which also means kind of past and future and everything is already determined in a way. So the water here going through the river already kind of the course it's going to take is already determined. This is kind of something that we kind of, that started at the beginning of the scientific revolution. If you think about orbitals, so if we want to look at how does the moon kind of move around the Earth, what we could do is, if we just kind of observe it, we just see kind of, okay, the moon is certainly moving through the skies and so on. Here we take kind of a picture from above, which we cannot really do that, but bear with me. So what we could do in order to better understand that is that we say, we kind of try to put the moon there at each time simultaneously. And what you can see emerging is kind of this circle that makes the orbital there, the trajectory of what the moon is going through. And kind of doing that so precisely that you see it's not actually a circle, but it's kind of an ellipsis is what kind of the great achievement of Kepler. So in a way, kind of doing exactly that, getting the geometric shape of orbitals is what's at the beginning of modern science in a way. We can do the same thing if we kind of throw a ball up and down. So we want to describe what's happening here. So we kind of chart where the ball is after certain times. And then we have this nice graph where we can see the ball actually kind of is doing a parabola, which of course is only the tip of an ellipsis in a way. So it's kind of the ball would be circling around the center of the Earth, but there's kind of Earth in the way. So it's just doing this parabola. But anyway, kind of the important thing here is what we're doing is we are freezing time. So time becomes something like a spatial dimension. It's just, we can see everything at the same time. So we can see the geometric shape of motion. And so we go from what's inherently time sequential and put that into space in a way. We do that kind of all the time. So it's become really second nature. And it's one of kind of the greatest theories in physics that we have these days, with this idea of that we can marry and really kind of put space and time together to have this space-time continuum with kind of relativity theory coming out of that. And I mean, that kind of this works in order to predict what's going on in the universe has been confirmed by many experiments. So it seems like it's really a good idea to do that. But what we're doing in a way is saying that time as such is kind of an illusion, because if we can say that time is really just a spatial dimension that we're moving through, it's in a way that the future is already there, it's already determined. You can make a much stronger argument if you bring in really the entire cosmological and relativity theory arguments there. But really kind of in this picture, there is no real actual time as we perceive it. It's just another dimension in the space-time continuum. So somehow time as we perceive it is just an illusion. It doesn't exist. Now, let me contrast that with the idea of time as something very real in a sense, where we say kind of time runs. So time is going from one moment to the other. And we come to this idea if we say time is kind of the interplay between states. So for instance, we have night and day following each other all the time. We can't have night and day at the same time somehow. These are all kind of, there's a huge qualitative difference between the two. And because we have these states changing, we can start and count it. So we can even build clocks, because we can say, well, there's kind of something going on here. I can count how many states are going on. And kind of with that, we get to a completely different nature of time. If you think about it in terms of the music, say, it would be completely silly to do the same thing as we did with the moon orbitals. So if you take kind of a nice, I don't know, a Mozart etude or whatever, and you say, well, let me just play all the notes simultaneously, I'm not really sure kind of the acoustic fidelity would be that much heightened, or that we will gain much insight from that. So somehow the reality of time here is essential for music to unfold, to be there. And we have this going from one state to the next as a very fundamental thing in the universe. This kind of becomes apparent if you look at quantum theories, for instance, where suddenly we cannot ignore time in the sense that we do in relativity. So we have a lot of this randomness. If we talk about kind of atoms that kind of decay, we have these half times, because we do not know when exactly they're going to decay. It's just going to happen at some point, probably between now and the next 10 million years, but no one can really tell. So time here suddenly becomes really one of these most essential things. And I think that's one of the main problems or issues why it's so hard to bring quantum mechanics and relativity theory together to one unified picture of the universe. So in a way, if we kind of look at time from this perspective, time is not an illusion, but it's kind of the most fundamental, the most real thing about the universe. So we have two kind of pictures of time. And my kind of argument or claim is that these two perspectives of time correspond quite well with how mathematics and computer science approach the same thing. So on the one hand, we have the dynamic view of the world and a kind of the static view of the world in terms of time, where I would say the dynamic view of the world is kind of what we consider computing, where time is really real and kind of the essence, whereas the static way of seeing the world is more the mathematical way. I mean, mathematics is kind of even static. If you think about it, once a mathematical theorem has been proven, that's for eternity. That's not going to change. That's just very kind of a thing that is, and this existence of theorems is completely outside of time. Whereas in kind of, if you read any paper basically in computer science, it's always about performance, making things go faster and so on. So time is really that core building block of computer science. So let's look at it from kind of the perspective of algorithms and what it means. So one of the problems that we have, of course, is writing something down means it's static, up to the point where you think of these hieroglyphics in stone or something. That's like for eternity, as kind of far as we as humans are concerned. So how do we write down something that constantly changes, that's kind of not fixed in time in a static manner? And we have kind of, this problem is not new for computer science, because music, for instance, had this problem for centuries and found kind of a solution of how to deal with it. And sometimes we feel kind of we're just doing this in order to make machines go. But in the end, programming or kind of algorithms is so much more than just make machines go. It's really a question of how can we capture this idea of, hey, we have something that goes on in time and we want to make it visible. So it's much more than that. And this relationship between time and between the static and the dynamic aspects of programming, say, or algorithmics, could also be likened to if you build this marble run, or kind of like the river that you have. You start out with building something static, but what kind of the entire thing in the end is not about the static structure, but much more what happens to the marble that you kind of have going through that. So even though we're building static structures, it's all about this dynamic thing that comes in afterwards and runs through our static system that we built. So this becomes particularly apparent if you think about, for instance, how branching works. Because in music, for instance, it's mostly just you follow a recipe and go through with it. And in computing, we have branches. So depending on what's going or has gone on in the past, or kind of the environment or whatever, we might take different branches and do different things. So we do not know where does the future go. And in computing, we can kind of have programs or algorithms that deal with that. Whereas in mathematics, you need some kind of a static way of looking at that. And that gave us the probability theory, where we try to kind of capture this idea of different possibilities with a static concept. So if we say kind of I roll a dice, I have these different outcomes, but I kind of try to capture them by saying, well, each of these possibilities has a probability of 1/6, say. If we go beyond branching actually and pick up this idea of this dice rolling or something, if you look at randomness, let me kind of make a very bold statement here, perhaps even to spark a discussion afterwards. I would say mathematics is really, really bad in dealing with randomness, because somehow you have to cast it into static structures. And the idea that something is completely random and you cannot predict what's going on is really counter what mathematics is doing with kind of trying to eliminate time and just look at it, look at the geometry of it, look at how it kind of is in its entirety. Whereas with computing, we can bring in a new perspective where we can embrace this idea of randomness. Let me give kind of an example here to highlight this a little bit more. I'm going for the Euclidean algorithm here. So you have these two gears, and the idea is how big do we have to make one of these teeth so kind of that the entire thing works. So we already know kind of the answers to the Euclidean algorithm. We have the greatest common divisor that we need to compute. Now, if you look at kind of what Euclid did back in the days, was mostly a geometric approach and afterwards kind of an arithmetic one. But the geometric approach was kind of you take two lengths and you subtract the length, and then you take kind of the smaller two pieces of this length and kind of subtract them again. So that's kind of the algorithm written down here. Of course, you can speed it up if you use division and modular operation with remainder and so on, but kind of the essence here is just you subtract things. The interesting thing that Euclid kind of then ask about it is there always a solution to that? So given any two lengths, we'll always arrive at kind of the greatest common divisor, so a common kind of factor length that I can put into the other ones. And kind of he then says, if that actually that never happens. So if I can go on to infinity and I never reach kind of the smallest parts, then we call the two lengths incommensurable. So not comparable in a way. And this kind of, I would say, this really shows difference between kind of mathematics and computing in a way, because from a mathematical standpoint, we just kind of look at two lengths and say, well, either they are commensurable or they're not. But that's intrinsic in these two lengths. That's there or it's not there. Whereas from a computing standpoint, we're thinking more about the time, kind of this algorithm going on. So if I try to compute this smallest length, will I ever arrive at a result? And can we actually know whether two things are commensurable or not? So in computing, we have such kind of, if something never happens, questions. So we want to know if kind of we have this algorithm or computation or whatever, can we just go on forever, or kind of will there be a solution, or what's going on there? And that's what kind of computing really gives us. So beyond just saying, okay, well, I have to length or whatever that are either commensurable or not, I can kind of ask questions. So can I actually answer that with the tools that we have? So can we find a solution? And even kind of versa, what we found is that sometimes we just do not know, and we cannot know whether there's a solution, so whether this algorithm will hold or not. The problem is we do not even know for certain whether an algorithm will just go on forever, because sometimes an algorithm could just go on too long. So you know the problem, right? If I ran an algorithm and it doesn't go kind of a program and it doesn't give me an answer after an hour, I still don't know, is it stuck or will it kind of give me an answer in the next 5 minutes or something? So we have kind of an entirely new problem here that goes beyond just saying this is the relationship between two things, or this is kind of an intrinsic property of something. So let me come to kind of education, perhaps kind of the part that we're very interested in here of this entire philosophical question. And let me start with a very well-known example here. So this x equals x plus 1 is kind of well known in our community as one of the things that are really puzzling in a way to beginners, but sometimes also to others. Because from a mathematical point of view, this is just an unsolvable equation. Whereas from a computing or programming point of view, this absolutely makes sense and increases x by 1. Because the thing is that we actually think of like an annotation. So what we have is on the right-hand side, we have something that comes before in time, and on the left-hand side, we have something that's afterwards. So we have kind of a distinction between two time frames, even in one line of a program. Whereas in mathematics, there's no timeness in any equation, so to speak. I think this becomes very apparent if you look at variables and assignments. Because if you think about kind of variables and assignments, so if you have kind of this three equations in a way here, from a mathematical point of view, you would just say, well, what it means is that the three variables A, B, and T all correspond to, or all have the same value, that correspond to the same thing in a way. Whereas from a computing point of view, we absolutely recognize that as that will swap the values of A and B. So it's kind of a meaningful algorithm that we have behind these three equations, because we have a time sequence in it. So in mathematics, what an equation or kind of assignment or whatever does is it entangles two things. So if we have this y equals 2 times x, whatever x is, y is twice as big. Whereas in computing, we don't have this entanglement of equations, but rather we copy values. So this y is 2 times x means whatever x is, you kind of you can compute it, and you have a new value y that corresponds to twice that much right now in this moment. But afterwards, what's going on if I change x or whatever, that doesn't influence y anymore, because I've already measured, computed whatever y is. And that's kind of a problem, this two ways of looking at the same things for students. Let me illustrate that with kind of two examples that I found in my classrooms and data sets. So here's an example where I ask the students to write a program that solves quadratic equations. And of course, you have this very famous formula to solve them. And the students are familiar with that when I ask them to implement that. So what they kind of some students do is they understand that they have to check the discriminant, that it cannot be negative because you can't compute the square root of a negative number. But still, even though from kind of a mathematical point of view, what they're doing here is correct, it will blow up, because in the second line, it tries to compute the square root even before kind of the testing in line 3 comes. So somehow kind of this idea of time when what is happening is kind of distorted in this picture. Another one is when I ask students to write a program to draw a graph, or sometimes I gave them a program and asked them kind of what graph does it draw. I get kind of this program here. So the graph is intended to be a parabola. This y equals x minus 10 times x plus 10 divided by 50. And the idea is you put the coordinate on the kind of a very left, and then you just by step go through and paint the points and by connecting lines so that you get the graph. However, what this actually will draw is of course the dead function. So it's just a line. There's no parabola going on, which is kind of course due, because in mathematics, if I change x, y will change with it accordingly because of this entanglement. Whereas in computing programming, we have a completely different notion of what this line 2 with y equals something does. It's so kind of what I found is that sometimes this mathematical pre-knowledge will in the programming or computer science classes lead to students' programs kind of blowing up. So they have these conceptions from mathematics, what a variable, for instance, or an equation or whatever means, and then they realize, okay, somehow it doesn't really work. So this kind of just blindly taking concepts from one field to the other doesn't work. So mathematics and computer science seem to have speaking of the same concept, but really they're not. They're just using the same names. Another instance of that is functions, for instance. So in mathematics, a function is something really very static. It's just a mapping where if you look here from going from the top to the bottom, it's just kind of the tracks are all there, they're given. It's clear that wherever you start, at what point you will come out. It's just this very static picture of what a function actually is. Whereas from a computing point of view, function is actually more like an algorithm where I put something in on top and I crank something and I have a process, and in the end I have the result coming out at the bottom. But it's kind of the idea of what a function is something completely different from mathematics. So again, kind of even if we're talking about the same thing superficially, what we find is that actually the underlying concepts might be completely different. And I think that's really important for computing education, that we make that explicit, that we talk about that with our students and make sure they understand these differences. And it's also, I think, a great opportunity in discussing these differences to really kind of make it more clear what is a variable, what is a function, and so on. So kind of to summarize or sum up the entire thing with a picture here, I think kind of mathematics as a very static thing is kind of the bedrock upon which we build most of kind of our scientific endeavors. And in no way do I want to bash mathematics or something here, but I think what computing can give us is this dynamic thing, this living thing on top of it, so that we recognize not everything can be captured by looking at the world statically, but rather sometimes we have to go for a more dynamic approach where things can change and are allowed to change or supposed to change. And we want to capture how something evolves, how something moves through time, so to speak. So thank you very much.
Yeah, thank you, Tom. Sorry. Thank you, Tobias. So when I'm listening to you, it's I mean, in some sense, I think I can hear different stories in a way. I can hear that, well, math and computer science isn't really the same, so it's something we could. So maybe we should think about how much should they really be related, or is it just confusing to try to relate them? But I don't think that's your message, right? I mean,
So I would say kind of my message is trying to figure out what's really the essential difference between the two fields in a way. So why should we teach computing at schools? And a bit what I want to say is that computing actually, even though it might look very mathematically, it does bring in a new element to the table. So it really does extend, enhance what we already have with mathematics. It brings in something novel, something worthwhile considering. And of course, there's a lot of overlap. So I'm not saying the two things are completely distinct, because we're using a lot of mathematical languages, of course.
No, I think it was a nice thought-provoking piece you had there. And I guess I'm more thinking of maybe I was expecting that you should say, well, you can more or less just do math because computing is just a version of math. but that's not what you said. And so I was, sorry, Lars-Åke has his hand up. Can you?
Yeah. So I had two spontaneous reflections here. So background here is that I give a lecture to math students, math teacher training students every year, where we talk about the relationship between programming and mathematics, and bring up some of these things like the equality signs, and that it means different things in different disciplines and such. I think your comparison between math and imperative programming here is a little bit limited, because if you would, for instance, compare math to logic programming instead, like using Prolog or something like that, you would find completely different relations here, because I mean, you have different classes of programming languages that have different designs and different inner mechanics, and comparing imperative programming to the logic framework of math, those are obviously very different. And I think it's it's a relevant comparison, because what kids in school get to learn is usually imperative programming. We don't teach them Prolog as a first language, but I think it's hard to make any general statements about programming versus mathematics, since programming is a very broad field in itself, and there are different paradigms of programming. So that was just a side comment. One thing that I think is very interesting when it comes to math and programming is that when you do programming, and when you get a little bit more advanced, once you have done Hello World and all that, when you write a computer program, it's very often that to not build your program entirely from if then else statement, you want to express what you want to do in your program in a mathematical way, if you understand what I mean. So you want to kind of generalize what you're trying to achieve in your program as a mathematical formula or function or something, to make the program more feasible to implement as well. And I think that is a very interesting relation between programming and math, that in order to be a really good programmer and to program very efficiently, you need to be able to do mathematical reasoning and express what you actually want to do in terms of math. So I definitely think it's wise to teach programming within the math subjects, because there is this relation, unless you want to build programs just consisting of if then else statements for all possible cases. Then you rather try to express it mathematically. So I think that, yeah, there are relations between math and programming, and I think it's very interesting to discuss them and make sure that kids understand these things that you raised, that now when we're moving in the programming world, the quality sign isn't the same thing as in the math world. And I think it was very interesting, this thing when you add time as a dimension. I haven't really thought of it that way. So I'll probably bring that up in my next lecture to the math teacher students. So, but thank you for an interesting presentation.
Yeah, thanks. So just kind of to respond to that, I haven't really that much experience in logic programming or whatever, but I hear the same argument with functional programming, which is also kind of very mathematical in a way. But if you actually look at it, so the idea of functional programming in a sense, or kind of the lambda calculus that's behind it, is essentially that you say we have the program as something, and we start to modify the program until kind of like in a mathematical equation, we see kind of the result of it. And what's the programming part of it is kind of the steps in between simplifying the program. So somehow these time steps, they're still there, but they're now implicit rather than explicit, like in the imperative style of programming. But still, kind of the computing aspect of that is kind of the question of how many steps do I need to simplify that, or what kind of simplifications can I make automated for the entire thing. So it's a different perspective on the entire thing, but these this idea that time is still of essence from a computing point of view, I would say is still there. And you can actually see that. So if you take Haskell, for instance, which is kind of a very pure, sorry, not poor, pure. Yeah. Sorry, a bit of it's not a Freudian slip in what you might think of. It's just a German pronunciation. So anyway, so as a very pure functional programming language, what you need almost immediately is this concept of monads and all that, so that you can deal with the time aspect that you have to bring in. And otherwise, you kind of relegate it really to just be a tool for handling mathematical expressions. And of course, I mean, the machines that we built, they were built as computing machines, something to help in mathematical endeavors. So both kind of, the interaction there is very fertile. That's also why I loved this picture where kind of the ocean comes together to this rock, because when both worlds come together, you have something interesting going on and something really that's happening here. So I do not want to focus too much on what the equal sign means or something, but more the message that time is something that really comes in, even if you do functional logic programming or whatever. Time is a new element that's essential key element for this entire thing.
Well, I don't fully agree on that, but if you haven't done any logic programming, maybe we shouldn't discuss that. But I can just briefly say that if you have a logic programming language, what you do is that you declare facts. You declare like the equivalent of lemmas in mathematics, and then you work from that. So you don't really have a time domain in the same way in that kind of language. And that was the point I raised that. But yeah.
On the other hand, I think what you do in programming, or one of the things we talked about when we created the IT program in the mid-90s, was that computing or IT, that's when you create things. When I think when you say create, you get into the time aspect, and I think maybe whatever programming paradigm you're using, you still do programming in order to create something, and then I think time comes in, whereas I don't think math has that property. But I think this is. But maybe if you take your presentation now, Tobias, and what would the consequences be if you think about it like this? I mean, now and then I would hear someone saying, a computer science program or computing program, it has to have math, otherwise it's not real. It's sort of, it's not computing. And then I remember once, I think it was in Brisbane, at one of the universities there, and they presented their curriculum, and they had no math, explicit math, in their curriculum. And so I asked them about it, because we had such a discussion at home here in Uppsala, where math is kind of king. You have to have a lot of solid math in order to do computer science. And well, talking to them, it kind of turned out that yes, they didn't have explicit math courses, but they did have quite a lot of math in courses that had different names, kind of hiding that you had math. And I think one of the reasons they brought up was they didn't want to have people to be scared of their education by putting a lot of math in there. But maybe this is not really what you talked about, but I think there is this interesting discussion about how is the relation between math and computing or computer science.
To add to this point, actually, it's interesting that you raised that up because I've worked at universities in England and in Scotland as well. And these conversations always happen because they're worried about not attracting students, particularly underrepresented students. We can have a conversation later on about, the words that are used in marketing, for lack of a better term, courses, and the reason, and their implications saying, oh, if you hide math, we'd attract more people because that implies that they're not smart enough to take math. So that's not the point. The point is, there are so many, particularly in Stockholm, I noticed in the undergrad in the subway, there are these startups and they offer programming or coding courses. And a lot of them, they give the impression that they're not going to teach you mathematics. They're just going to need to teach you what is necessary to become a computer scientist. I mean, I looked into the websites and they're not even computer science, but there's a clear disassociation between computer science and math. So how would you respond to that?
So just first of all, I believe very, very much that mathematics is absolutely necessary to become a good computer scientist. So I'm not kind of going in any way against that. More that, I mean, if we think about kind of when we want to discuss, let's say, algorithms in a way. So what we're doing is we're looking at dynamic procedures, dynamic kind of things as static objects in a way. And so we need the mathematical language to really understand and work with the entities that we're dealing with. Just as kind of, it's so, is there a mathematics class or something on earth that never teaches an algorithm? Of course you teach them Euclidean algorithm, even though it brings in the time thing. So kind of there's no clear separation or distinction between the two. And somehow I've seen this with others as well. So for instance, let's do physics without mathematics because people are scared of the math and won't go into physics because of that. And kind of I feel equally that's kind of a futile attempt because you miss out one of kind of the greatest tools that we have at our disposal. And at the same time, so I recognize, yes, kind of people want to hide the mathematics because of these marketing reasons, but I don't think there's a philosophical or educational argument that really stands its ground that you can do away with mathematics for solid computing education. I don't know, does that answer your question or am I?
Yeah, but also Daniel wrote a comment, no?
Yeah, that we teach algorithms to first grade. But I mean, as some of you, but not all of you know, I'm responsible for an engineering education in Uppsala. And I mean, I've been told by our marketing experts that I shouldn't mention all the math that we have in my program since that wouldn't attract as many women to the education, which I think is just a stupid viewpoint on this.
Very dumb.
Yeah, but the thing is that I also talked to students that said, okay, I want to learn IT. I don't want to do math. And they say, I want to work with machine learning, but I don't want to use math. And it's like, okay. So it seems like math has a very poisonous terminology term for many people before they come to university. Many, when we talk to new students about math, they think about all these horrible math sessions that they've had during primary and secondary school, where they sat and didn't understand. They don't understand the full width and the full potential of math, and that there is actually some aspects of math that they haven't met yet that is really cool and essential to be a good computer scientist. So I think math in itself has a marketing problem, because if you go out, I know they did a study in Sweden when they went out and asked 30-year-old people what they thought about school, about math, and about 80% thought that they hated math. from school. And I think there lies a big problem that as soon as you start talking about math, people get they get inner images about something it doesn't necessarily have to be.
But I would argue it's actually bigger than just math in the sense of, have you ever noticed how many programs kind of promise that you can learn a new language without having to go through grammar? So, which is kind of a very similar picture. Everyone wants to speak a language, but please no grammar, because that's hard, that's kind of abstract and so on. So I think kind of that's more or less a universal phenomenon where we just, I would say culturally concentrate too much on the outcome and neglect that kind of building up how we get there is actually an important part. That's I mean, just going a bit on a side note, sidetrack here. I think that why this entire ChatGPT discussion hits us as pretty hard, because we've been really focusing on these outcomes, on these artifacts. So you kind of just do an exam or an essay or whatever at the end of and we kind of assess you on that, and suddenly this just breaks down. Whereas as kind of the way I experience good education is there's a constant dialogue between a teacher and a student, and you kind of talk about the thing all the way through. So it's not just the thing in the end that we kind of off look at. But that's just a side note. So I think yes, it's kind of mathematics that has this marketing problem, but it's not just the fault of mathematics or mathematics alone. I think it's in general that we try to avoid any rigorous things that kind of spell out you have to put in a lot of effort in order to master it. Just kind of a small kind of I should say a remark about that is that, for instance, Knuth said in the 70s that we should computer science education into schools, because computing has actually the power to make math come to life. Because if you just instead of teaching all these mathematical facts as like these static dead things, you can bring them to life with these dynamic aspects of that computing brings in. So here you have another opportunity where computing and math can have a very fertile interaction.
Yeah, now I think this is taking a bit of a different direction. But I think what you're saying, and I agree, maybe computing could be a way to save math rather than math being something very needed for computing. But maybe one can look at it from the other point of view. I mean, like you said, that people hate math, and you have people saying, I didn't understand anything. So when they mention math, their brains they freeze. But when you talk about money, doing the same thing, the brain works suddenly. And maybe computing could be a way of making, as you said, math more alive, more meaningful to many more people.
I can say a very concrete example of this, I think, is in Sweden in year 1 to 3 in primary school, when kids are 7, 8, 9 years old. They do some first programming, and they usually use this programming language Scratch, which I guess most of you are familiar with. And after having used Scratch for a week, it's natural for them to work with variables. It's natural for them to use with the coordinate system, where you have the x-axis and the y-axis. And it's natural for them to express movements of these figures in terms of mathematical operations. And what's been studied some, and I also talked to some teachers about this, is that when they later meet these terms in a mathematical context, like when they start with algebra a few years later, when they start with functions and everything, they can relate to what they have done in the programming context before, and the mathematics become a little bit living, but they just didn't understand it was mathematics until they started to theorize that in the mathematics courses or classes. So I think here we have an interesting thing that we didn't have 20 years ago, that pupils can first meet mathematical concepts without thinking of it as mathematical context, but they think of it as programming language essentials. And then when they meet it in math later, they just think that this is easy. I did this in programming. And this is something that we observed, and I think it's very interesting.
Indeed. Yeah, I can say that kind of happened to me. I started programming quite early on, so I'd already experienced functions and variables by the time we got to algebra in like 7th, 8th grade, whatever it was back then. So it's true, as you say. But I would say also that opens kind of the inverse of the problem, because one of the problems, as mentioned here, is that the students, I mean, usually they have maths and then they come to programming, and then they have this problem of understanding the statefulness, as I call it, in programming, or the time aspect. As we said. So I suppose if they first learn programming, I mean, they have that problem in reverse, I suppose, because then they know this statefulness, but the equations, they are stateless and just relationships that are stated. So then they would have to learn it the other way around. But in either case, I mean, we need to highlight these things. And actually, I'm doing a study with one of my TAs that's kind of ongoing. And we were looking into all kinds of misconceptions in programming, and analyzing them from a variation theoretic point of view. And this statefulness of programming actually came up. So I mean, we do indeed need to cover it. So I mean, one of my conclusions is that we really need to show this early on with proper variation, to follow variation theory. To illustrate the difference between maths, this statefulness that we have in programming that we don't have in maths equations and so on. Because I realized that quite a few of these misconceptions that were reported in literature kind of stems from this one. Because, like, for instance, when they first of all, they can put the statements out of order because they think they are relationships just like the equations in maths, and there it's fine. But also they have this misconception that if you have a variable assignment, and you try to use it later, and you change one of the variables that are used in the assignment, one of the dependencies, that the value of the variable is updated later, which it isn't, because of the statefulness. And it occurred to me that, I mean, that probably stems from also this part from maths, where it's all relationships and you don't have this statefulness. So it's actually quite a few misconceptions that occur that I think are related to this very thing.
Yes, absolutely. First off, I can echo this, that I too started with programming very early, and I found kind of most of the stuff in mathematics kind of pretty easy because I had seen it in programming. But yeah, I've never thought about kind of the reverse, but I guess we will have to work together with mathematicians in the future, because if students are going to learn programming very early on, and they will transfer notions about these concepts to mathematics, that suddenly it's on part of the mathematics that they have to deal with these misconceptions as much as we do. But yeah, kind of these misconceptions that you mentioned, I observed the same thing.
James put a comment about song composition as a mean of teaching programming, and you had music as well in your presentation.
Yes, so one of my PhD advisors, Bill Manaris, is doing research in how to teach programming through music composition. So I've seen him doing that in class, and it's incredible. I think I had never thought about that before. I'm certainly no musician by any means of the word. So that was kind of an alien world to me. But on the one hand, I think it shares this timeless component. And on the other hand, I think that's what Mats brought up before. If you bring in the music component, it's again kind of this being able to construct something, to express yourself, to really do something that's your own thing with computing, and that makes it a very powerful tool in education.
Yeah, certainly that agency is important, so the kids can see, you know, of course, some outcome to happen. I think the other thing that relates to what you were saying, it's a very natural notion of sequence or time, because I think part of the thing Daniel was saying earlier about this statefulness being sort of difficult to sort of impose on top of a mathematical mindset, because it's still rather abstract. We're still talking about some assignments and values, which are very sort of abstract concepts. Music is something that kids just get naturally, and it's a natural form of a sequence. And you do the notes out of sequence, it's clearly different to the notes are in the opposite sequence or something like that. So I think it's that intuition that gets them into this natural thinking about sequence and state and if you like, therefore time. I mean, you could probably argue what's the difference between the notion of sequence, the notion of state, and the notion of time, and you probably have a very straw-splitting debate about how that all works. But I think that's part of it. It's a very, in some ways, a more concrete representation of a notion of sequence than some sort of abstract notion of executing and changing values of variables in boxes and all that sort of intuition we often use. I think one interesting challenge, though, is I think Matt's mentioned about could computing save mathematics. Well, what do we teach in schools about computing? Is it part of mathematics? Is it something separate? Is it a thing like physics and maths are somehow interlined, but we tend to have separate subjects and things like that. So I think there's a lot of things to play out over the next little while about, do we teach this thing that includes computing and mathematics as one unit? Are they conceptually separate? And can you be good at one without the other, or vice versa? So I think there's a lot of interesting things to unpack over the next few years about how we approach things certainly at secondary level and therefore at tertiary.
Yes, absolutely. I think if we're probably and hopefully just at the beginning of figuring out what exactly to teach in schools to make an impact, because at the moment I think if there's great ideas around, but we probably just need to try out and see what's happening, doing our best.
So, when you talk about math, there is an ongoing, I think, debate if programming is more a language thing or a math thing, if you know what I mean. So I worked with a neuroscience person, and we taught novice students, high school kids, a bit of programming, and then we put them in the fMRI camera. And we gathered lots of data from them, like their grades from year 9 in school. And when the neuroscience person, not me, looked at that data, it was mostly the language areas that were activated when the students were reading code and answering questions in the fMRI camera. And when we looked at their grades from school, both language and math were very strongly correlated to how well they learned, but math was a little bit stronger correlated. This was one study, and the students we had in that study were very much math students. I mean, they were on a national science programming in high school. So, but it is, it's interesting to see it was the language area that were mostly activated. It was also interesting to see that both language and math grades from school were very strongly correlated to programming. So.
Yes, so I'm familiar with kind of this. I think Jeanette Siegfried in Germany has also made kind of some of these studies of fMRI.
Yes. They might have because we read the studies that were around on programming, and some of them were on experts. And so I think we really carefully selected novices. They were between 17 and 18 years old, something like that. So it's a little bit different, but there are a few studies that say the same, that the language is, yeah.
I mean, I don't think I can really say much about this as kind of an expert or something, because it's not in that sense my field. But kind of what comes to mind a bit is the struggles that we still have as a community to define what computer science is. So is it a mathematical discipline? Is it a science? Is it a field of engineering? Or whatever. So it seems to be a very interdisciplinary thing that's going on, and particularly in education, we kind of touch upon that with the music and all that. We have a lot of arts coming into this mix that's probably absent from kind of what we think of it as the scientific academic discipline that we're engaged in. So there's so many things coming together in computing education in that sense, that I'm not really surprised that various different aspects are correlated. And kind of there's also, of course, the G factor in intelligence that's also correlated to all these things. So I mean, everything is correlated to everything else in that field up to a certain degree. So I'm not really surprised at what you're saying, but I'm not sure I can really contribute much to that.
But what I wanted to say, like, maybe we shouldn't try to define it. Maybe we should go in and say, well, computing is really a lot of different things here, and it means different in different contexts. And maybe trying to be a bit more clear about which version are we talking about. Because otherwise I think we're going to be miscommunicating. If you kind of have a very particular view of what computer science is, and you talk to someone who's a rather different view, then you're never going to agree. And maybe that's not constructive to try to find this is the definite definition, because I think that's it's going to be more or less impossible to do. And maybe it's if you look, if I'm what you say in Swedish, kidsar, make a guess, is that if you're activating the language center or the math center, it's kind of might depend on what are you trying to do with the programming. Are you dealing with the time flow version or the static time version? Maybe that would, if you would do stuff that would more mathematical, then maybe the language center would be, I don't know, language center seems more time, like music.
But
sorry, Anna wanted to say something, and kind of perhaps she wants to respond first before Mats said something.
You mean did you say my name?
Yes. You just wanted to speak before, and
yes, I tried to say something because I mean, we found that the language areas were there that they were most activating, but what does that mean for teaching and learning? That is still an open question. So I'm looking at the text that I wrote, the result from this huge study, and where the researcher from neuroscience say that Broca's area in the brain, whatever that is, which is a language area which is involved in simulating the code output when the students were simulating code in their head and answering questions. Its activity predicts long-term memory performance. So it's a complex process here, and we don't know really what it means yet that the language areas are more. It's not like, okay, now we know how to teach it.
But we know some aspects of it.
I was thinking when Mats talked about these things that to our students we also make it very clear the distinction between understanding computers, how they work, and using computers to understand something else. And I think we have this duality. On the one hand, we want to understand. Well, it's the same for math, actually. On one hand, we want to learn math. On the other hand, we want to use math to learn other things and understand other things. And but in order to be able to learn programming and computing, maybe we have to use some other things that we already know or doesn't know as tools. So and these are the interrelations that we're talking about. That it's one thing to understand how a tool works, but it's another thing to use that tool to build or understand something else. And I think it's an intricate web here on what comes first and what should we teach first and how and everything that needs to be carefully planned and executed in school so that they come to us well prepared with a good understanding in both math and computing, so they can use them as tool and also maybe understand more about it.
So I've been part of a study where we looked at the role of math in different areas in STEM education. And there is plenty of study that shows that the students' understanding of the role of math in physics and also in chemistry is very important for how they learn. There is some studies from high school and school level that shows that teachers' understanding of the role of math influence the students' understanding of the role of math, which influence how they learn. So we did a phenomenographic study, which I think Daniel knows what it is, I heard, on teachers from different areas. And there was one from computer science, and then there were some from physics and chemistry and geoscience. And we have done a preliminary outcome space on teachers' understanding, university teachers' understanding of the role of math in their areas. And there were surprisingly similarities across computer science, physics, chemistry, and geoscience. So we have a nice outcome space here. And we will argue how important it is that the teachers have a good understanding of the role of math and in their subject areas. Otherwise, they cannot teach the students, and that will influence the students' learning. That might be in line with what you talked about, Tobias.
Yes. So first, I really like this distinction between using it and kind of studying the same thing. So and kind of thinking back, I'm just kind of to respond a bit to Lars Åke's distinction here. I feel very lucky that I had two math teachers in my high school. First, it was an engineer who really taught us about kind of how to use mathematics to solve some problems. And well, yeah, pi is about 3 and that's okay. And we need to solve a problem and get some results. And then we got kind of one of these very philosophical, pure mathematics teachers who really went down in this. So I had both aspects, and I think kind of they're both very important. And what I'm kind of wondering at this point is, what does it mean for computing education in school? And I think if I understand you correctly, Lars, okay, you're not just talking about using computers as a tool in we have to teach Word or something, but something more kind of a bit more substantial.
That is right. We use computing as a tool to explore some areas of math, for instance, like graphs, probabilities, stuff like that. So first kids learn how to program, and then they learn how to use programs to explore things in various subjects.
And kind of coming back to what you said, Anna, I'm not entirely sure. It's been a while, but there's kind of this study about the role of variables. So that if you're aware that the kind of variables or the equal sign or whatever has different roles and meanings depending on context, even if you're just aware of as a teacher, I think that really improves your teaching and an understanding of it. So yeah, I think to me it makes perfect sense that particularly if as a teacher or educator, the better you know the role of what you're using, why you're using it, the more effective you can be as a teacher.
Yeah. Do you refer to Dermot Schindler's Kennedy from Ireland? I put a reference. He has written a lot about state, you know, and so I think his whole thesis was, I might be wrong, but he looked at, he started with threshold concept. I don't know if he left that idea later on, but he's talked about this state and assignments and assigning variables. I think.
So I have a question to Tobias here. When I talk to primary school teachers about programming and how it relates to other subjects, many say that they think that programming is a very creative thing and process, and many of them think that it resembles maybe more of crafting in some aspect, like doing handicraft and the more like doing arts, painting, music, and all these things. Do you have any thoughts on that, how programming relates to non-mathematical subjects? I mean, Anna already mentioned the relation between languages and programming, but if you think about, for instance, crafting, slöjd in Swedish, is that something that is resembling of programming also? And
yeah, I think very much so. And so I think that there are various aspects to that. So if you really talk to experts in let's say mathematics or whatever, they usually would describe the activity or work as a very creative thing they're doing. So it's kind of it's the same for an author who writes a book. That's a very creative process. And yet most of what we do in school at these levels is not really that creative, because you need to build the fundamental kind of tools for that first. Whereas in computing, I think we managed to come up with these programming systems that allow you to very quickly come to the point where you can express some initial creativity. And that's perhaps almost unique. But it's also so you have this constructionist approach from Puppet and so on. So as one of the first approaches to get computing across, where you really kind of emphasize this crafting thing. Just I think kind of that comes a little bit back to what we kind of talked about earlier. A hypothesis that I perhaps want to put up here is that the reason why computing can really help with mathematics in kind of making it more approachable, more interesting and so on, is because it's a much more active thing what you do with programming and so on. So rather than just talking about this theorem and saying this is how things are, this is what a function are, and we now learn to kind of I don't know, do algebra with it. You actually make it to a living thing that you can interact with. You do actively something, and active learning is what we actually want to achieve in the first place. So somehow I'm not sure I can really say much about all the different subjects and how they relate to computer science in that thing. I think there are very strong connections to the arts of obviously, to mathematics, to physics, and so on. So I've worked with quite a few physics teachers who are very interested in using programming to simulate physical experiments, say, for instance. So there's a lot